Everybody, tonight we're trying to prove something that I'm gonna take the time to state in a modular arithmetic format, and I could have just stated it that way. I'm not sure why I didn't actually, but anyway, what we're trying to prove is equivalent to this modular arithmetic statement, this congruent statement. 3 to the n plus 52 is congruent to 0 mod 59. And again, I could have put this statement exactly here, you know. Either way, they're equivalent statements. In my opinion, it's just easier to work with it in this format. Now, again, this statement is true for any n that's congruent to 5 mod 58, but we have to prove it. And y'all, just what this means is that this 59 will cancel with a factor of 59 in this numerator for all n is what it's saying. So we got to prove that, okay? Now, this modular arithmetic statement just means 3 to the n plus 52 minus 0 is divisible by 59, okay? And notice that 59 and 0 are the same thing, mod 59, okay? Now, so let's see how we can get started on this. Here we have 3 to the n plus 52 equals to this. Well, where did this come from? Well, if you recall, a modular arithmetic statement, any modular arithmetic statement can be just replaced with an equality condition. In other words, you can also, this modular arithmetic statement is equivalent to n is equal to 5 plus some integer multiple of 58. Okay, and that means that m could be 0. M could be any integer at all. Okay, so that's exactly where this business right here came from. Okay, n is equal to 5 plus 58, a multiple of 58, and that's exactly what this is. If you just remember your laws of exponents, remember we're using the result a to the mn, I guess, or wait, a to the m times a to the n, let's do that, right, is equal to a to the m plus n. And I'm overloading my symbols here, folks, but that's exactly where, if n is equal to this, okay, then 3 to the n is equal to this by this property of exponents. And again, these symbols, this n does not mean the same thing as this n here, of course. All right, so let's keep going. Now, 3 to the fifth is 243. That's not a very difficult computation. And when I say reduce, I mean reduce modulo 59. Now notice that 243 is equal to 4 times 59 plus 7. And that's the arithmetic statement behind going from here to here. That's why I like doing things in modular arithmetic format. You can treat things very much like equality symbols. So that's plus 7, right? 4 times 59 is what? 236 plus 7 is the 243 that you see. So this 7 got reduced to modulo 59. Okay, so that's all that really changed in the statement. But now, oh, I'm sorry, yes, we do have one other thing going on right here, folks, that's quite important. There's a result called Fermat's little theorem that goes like this. It says that if you have a raised to the p minus 1, that's congruent to 1 mod p. This is called FLT, Fermat's little theorem. Okay, now the assumption is that p and a are relatively prime. Let me write that down. A and p are relatively prime, and they are in this case. A and p have no, they have no factors in common other than 1. Okay, so that's what happened right here. If you take a look at this statement right here, it can be rewritten as 3 to the 58. This is the laws of exponents also. Raised to the m power, right? But per Fermat's little theorem, 3 to the 58th is congruent to 1 mod 59. See, 59 is a prime. Didn't mention that earlier, but 59 is a prime. And if you decrement 59 by 1, you get 58, which is exactly what Fermat's little theorem says. I'll call that FLT. Fried liver tips. No, just kidding. Fermat's little theorem. Okay, but anyway, folks, this 1 that you see right here is exactly, oh, I forgot to write 1. Sorry, my bad, folks. 3 to the is congruent to 1. Getting excited here. 3 to the 58 is congruent to 1, and let me put that parenthetically if I can possibly fit it in there. Mod 59, right? And this 3 to the 58 congruent to 1 is exactly an application, a special case of this Fermat's little theorem result. Okay, so this 1 that you see right here, gosh, I'm making a mess out of this. This 1 that you see right there is the very same thing as this 1 right here, but 1 raised to the m is just 1. And as we mentioned earlier, 243 reduces to 7. Okay. Yeah, sorry, that was slightly confusing. Hopefully there's enough written down to where it makes sense to you. Okay. Now, but notice right here that this sums up to 59. But 59 is congruent to 0. Okay. Mod 59 is trivial, right? 59 is congruent to 0, mod 59, and that is what we were trying to prove, folks. This guy right here. We rewrote this in this modular arithmetic format. We went through a little bit of arithmetic here for Fermat's little theorem, and we got our result. Okay, so right here, let me go ahead and just recopy this part right here. 3 to the n plus 52. Is congruent to 0, so we can go ahead and say, and of course it's mod 59, I'll leave that out. We can go ahead and circle that and say QED. Now, I want to just work a special case, one that I can actually do without using a calculator. Notice that, remember that this holds for any n, this holds for any n that's congruent to 5 mod 58. Well, 5 is congruent to itself. 5 minus 5 is 0, right? So notice for n equals 5. For n equals 5, 3 to the 5th is 243. We already know that, right? So we get 243 plus 52 equals 245, or excuse me, 295. But that's equal to, we'll put a 0 for emphasis, 5 times 59, right? So this, of course, says that 295. 295, it's a terrible looking, 295 is congruent to 0. Sorry, y'all. Can we live with that 9 there? 295 is congruent to 0. Mod 59, 5 times 59 is 295. So that's a special case. Also, you could try it out for n equals 63, but you wouldn't be able to do that calculation in your head. You'd need something else, right? N equals 63, 63 and 5 are congruent mod 58, right? So, but in any event, folks, that's the end of the proof. I hope you liked it. I like it. I always like these kind of pure number theory sort of results that depend on Fermat's little theorem, Euler's tangent function, etc. Anyway, that's it. Thank you for viewing.